Hi. So the first chapter was a very short one, wherein we discussed about fundamental ideas of what CFD is, and we have reviewed basic concepts of fluid mechanics. Okay. In today's lecture, we will start discussing chapter two, which will be focusing on the procedure of finite difference method to obtain solution of governing equations. Okay. So the process of obtaining approximate solution to governing partial differential equations using any computational approach involves two stages, as we can see in the figure. So the first stage is called discretization. Okay, so the physical problem is described by the mathematical model, which is usually a partial differential equation. The first stage of a computational approach is discretization, which means that we convert the governing, usually partial differential equation, into a system of linear algebraic equations. Okay, so this for discretization we can employ either finite difference or finite volume or finite element method, or some higher order schemes called spectral methods. Okay, so no matter which method we apply, our focus is no, they will give rise to a system of linear algebraic equation from the governing partial differential equation. Okay, and the next step is to obtain approximate solution to the system of this algebraic equation. Okay, so we have started with PDE, we have obtained a system of linear algebraic equations, and these equations have to be solved to obtain the approximate solution. Okay, so so we know that computers cannot directly handle partial differential equations, but they can very efficiently solve algebraic equation if proper algorithm or methods are available. Okay, you have already learned about the methods to solve system of linear algebraic equations in your numerical analysis course. For example, Gauss elimination, Gauss Jacobi, Gauss Seidel, and successive over relaxation method, etc. You have learned many methods in your numerical analysis course to deal numerically or to solve numerically the system of linear algebraic equations. Okay, so in step 1, discretization step dictates accuracy of the solution. The second step, equation solver steps, decides the speed of your simulation. Okay, if you want your simulation to run very quickly, you have to employ a very efficient equation solver, and if you want your solution to be very accurate, you need to choose higher order or more accurate discretization schemes. Okay, so in this lecture we will be discussing about, the focus of this lecture is on discretization. In the next lecture we will be talking about the equation solvers. Okay, so so one more thing, it's a theoretical concept. We will be dealing in the entire course with a well posed problem. Okay, by well posed problem we mean a solution to the given partial differential equation exists. Okay, and the solution is unique. Okay, and the third one, the solution varies continuously with auxiliary data. Okay, by auxiliary data we mean initial and boundary conditions for the problem. Okay, by when we say solution varies continuously, what we mean is that a minute variation in the boundary condition will give rise to a very small variation in the solution. Okay, a small, if a small change in the in the boundary condition gives rise to a large variation in the solution, then the solution does not vary continuously with auxiliary data and the problem is not well posed. Okay, so this is a theoretical concept. You have to know what a well posed problem is. In the entire course we take it for granted that a problem, all the problems that we are dealing with are well posed problems. Okay, fine. Okay, so in this course, in this lecture precisely we will be dealing with one dimensional heat conduction in a rod. Okay, so consider a solid rod of length L. Okay, L is the length of the rod and alpha is the thermal diffusivity. Let alpha be thermal diffusivity. So the heat conduction in this rod can be expressed in general as alpha del square U plus the forcing term or the source term is 0. Okay, so here U, by U we mean temperature of the rod. F is the source term that adds or remove heat. Okay, we know the nature of the source term here. Okay, so F is a known function. Okay, for a one-dimensional problem, okay, this is a general vectorial equation. For a one-dimensional problem, this goes to alpha d square U by dx square is f of x. Okay, so that is the governing equation for heat conduction in the solid rod. Okay, so this is the governing equation. Okay, for complete specification of the problem, governing equation alone is not sufficient. Okay, we need, what else we need? Can you think? For complete problem specification, we need governing equations plus auxiliary data. Okay, governing equations describe in general the physical process. Your auxiliary data makes the solution makes your solution unique to the particular configuration at hand. Okay, by auxiliary data we mean initial and or the boundary conditions. Okay, so the current problem that we are considering is a steady state problem, so no initial condition is needed. Okay, only boundary condition needs to be specified. Okay, so initial condition for this particular problem is not needed because we are dealing with a steady state problem. Okay, so the physical problems that are described only by boundary conditions are called boundary value problems. Okay, you must be knowing all these things from your PDE course. Okay, and there are three types of boundary conditions. There are three types of boundary conditions. One is Dirichlet boundary condition. Okay, By Dirichlet boundary condition, we mean the value of the unknown is specified on that portion of the boundary. Okay, so value of the unknown is specified. For example, u in this problem is specified. Okay, that's a Dirichlet boundary condition. The second one is Neumann boundary condition. Okay, by Neumann we mean derivative or gradient is specified. Okay, so for this problem we can specify du by dx, which is gradient of the unknown, which is the temperature here, is specified. Okay, the third one is Robin or mixed boundary condition. Okay, so Robin or mixed boundary condition is the combination of Dirichlet and Neumann boundary condition. So this can be, for example, u, which is the unknown, plus some constant times the derivative will be specified. Okay, so in all these cases, so the constants, or it can be functions, they are known constants or spatial functions defined by physics of the problem. Okay, so we know these constants. Okay, so for this particular problem, okay, let us assume that the temperature is fixed at the left end. Fixed temperature at left end, which means u, the temperature is, let's say, ua, which is the known value. Okay, and the right boundary is insulated. Right end, by insulated we mean heat cannot flow through that boundary. This means du by dx is 0. Okay, so we have the rod here, okay, of length L and thermal diffusivity alpha. On the left end we specify the temperature to be a known value. Okay, so this is a Dirichlet condition, and on the right boundary we say it is insulated, which means the derivative is 0. This is the Neumann condition. Okay, so now we have the governing equation as well as the boundary conditions, so the auxiliary data. So the problem specification is complete. Okay, so to solve this problem using finite difference method, we need to generate mesh over the entire domain. Okay, and since we are dealing with the one-dimensional problem, this step is very straightforward. Okay, so we are going to do mesh generation, which means that we are going to cover the domain with a mesh that has a number of nodes. Let us consider 5 nodes, 3, 4 and 5. You can draw them as if they are equally spaced. Okay, so let us name these nodes to be 1, 2, 3, 4, 5. The distance between each of them is delta x. Okay, so the distance between two successive nodes is constant between any node, and that is delta x, and the total length is L. Okay, so this denotes node, and by node we mean spatial locations at which we compute approximate solution u. Okay, so the 5 points that we are shown here, as we will see in the upcoming discussions, that these are the spatial locations on which we are going to compute the approximate solution. Okay, and generation of these nodes and their interconnectivity data is what do we mean by mesh generation. Okay, so by mesh generation we mean generation of these nodes plus their interconnectivity data. Okay, this is what we mean by mesh generation. Okay, since this is a one-dimensional example, it is very, very straightforward. We will have some discussion on mesh generation in later classes. Okay, so now we are going to apply finite difference method here. Okay, so the main idea of finite difference method, okay, is to replace all derivatives in the governing equation by their finite difference approximation. So replace all derivatives by their finite difference approximation. So this is the main idea of finite element method. Okay, so but in this equation we only have a second order derivative. Okay, so this is the governing equation. We just have a second order derivative in the governing equation. Okay, so now the finite difference approximation to second order derivative is this finite difference approximation to the second order derivative d square u by dx square. Let us consider a node I which is connected to nodes I plus 1 and I minus 1. Okay, to approximate the second order derivative at node I, we write like this: u I plus 1 minus 2I by delta x square. Okay, so now we are going to have we are going to have a very detailed discussion on how to derive finite difference approximation in the next lecture. Okay, for now assume that this is correct. This is the finite difference approximation to the second order derivative. We are going to derive this in the next lecture. Okay, now we are going to apply finite difference approximation at every node. Okay, apply finite difference approximation at every node. Okay, so at node 1, let's take node 1. Node 1 is a boundary node, so the behavior of the boundary node is given by the boundary conditions, not by the governing equation. Okay, so governing equation for node 1 is simply u1 is ua. Okay, when we write u at I, we say value of u at node I. Okay, this is what this notation means. Okay, now let's go to node 2, which is an interior node. Okay, so this one we have already applied, which is a boundary node. Let's move on to node 2. Okay, so the governing equation is minus alpha d square u by dx square is f of x. Okay, so now this becomes, by applying finite difference approximation, this becomes alpha times d square u by dx square at node 2 becomes 2 u2 minus u1 minus u3 by delta x square equals to f of x 2. Right, so we have a second order derivative in the governing equation. We are at node 2, so we need to replace d square u by dx square at node 2, and from this expression here, okay, what we have is minus d square u by dx square. So we substitute I equals 2. Okay, because we need finite difference approximation at node 2, then we get this expression. Okay, by rearranging, we get 2 u2 minus u1 minus u3 is 1 by alpha times f of x2 times delta x square. Okay, so similarly at node 3 you can repeat the same procedure. You get 2u3 minus u2 equals to 1 by alpha delta x square. Okay, and at node 4 2u4 minus u3 f of x4 times delta x square. Okay, so then let's come to the last node, which is node 5, and node 5 is the boundary node. Okay, it is located on the boundary, and again this is not governed by the governing equation but by the boundary condition, which is du by dx is 0. Okay, now we are going to assume one more thing here. It's not really an assumption. We are going to derive this at a later point, but for our discussions, let us take for granted that du by dx at I is u I minus u I minus 1 by delta x. Okay, so at node 5 we have du by dx is 0. So the equivalent finite difference approximation is u5, because we'll substitute I equals to 5 here. So u5 minus u4 by delta x is 0. Now that implies u5 minus u4 is 0. Okay, so we have now one discretized equation per node. Okay, at each node we have discretized the governing partial differential equation and have got one algebraic equation per node. Okay, so what we have done as of now is that we have taken the governing PDE and we discretize it at every node, and that gives you an one algebraic equation at every node. Okay, we have 5 nodes and we have 5 equations. Okay, this can be written in matrix form. Okay, so in matrix form we have 5 equations. We are going to write this in matrix form. The first equation is this one, u1 equals ua, so that becomes 1. Okay, I'm going to write the final one, then it becomes very clear to you. Okay, minus 1 2 okay, times equals to ua f of x2 times delta x square by alpha f of x3 and this is 0. Okay, we have not done anything new. We have 5 equations, let's say 1 2 3 4 and 5. We have written these equations in a matrix form. Okay, so this is so this is A, which is system matrix. Okay, and this is U, which is vector of unknowns, and let's say this is B, which is the vector of source term. Okay, and you know from your high school classes that any system of linear algebraic equation can be written in matrix form. Okay, this is what we have done now. Okay, now what has happened as of now is that we started with the governing equation, which is a differential equation, minus d square u by dx square equal to f. Okay, but there is an alpha here. Okay, by the process of discretization, we have obtained, or we have converted, the differential equation into a system of linear algebraic equation. Okay, so there is a common misconception in CFD is to associate discretization with mesh generation. Okay, so you have to remember this: discretization is not discretization does not imply mesh generation. Okay, by discretization we mean converting the differential equation, usually partial differential equation. Here we have an ordinary differential equation, but in general we will have a PDE, and we convert the PDE into a system of algebraic equation. That is what we mean by discretization. Okay, so after attending this course, you should not say discretization means mesh generation. Okay, and we have one more point to make here. So this differential equation, whatever we have here, this is valid at every point in the domain. Okay, because it's a differential equation that you can apply this to any point. For example, for the given problem, you can apply this equation to any point on the rod, and that should be satisfied. Okay, whereas the linear algebraic equations are valid only at given nodes. Okay, so these are valid only at given nodes. Okay, at any point in between, let's say we have these 5 nodes, at any point, let's say here we don't have any equation. Okay, so we will obtain the solution at the intermediate point between the nodes by interpolation, which you have also learned in numerical analysis course. Okay, fine. So I hope this process of discretization is clear. If not, please stop this video and pause this video now and go back and start from here. How do we begin with the governing equation, and then how did we replace every derivative by the finite difference approximation, which gives rise to the system of linear algebraic equation. Okay, so now the discretization part for this problem is done. It seems very simple because we have taken a one-dimensional problem. For multi-dimensional problem, the process can be very complicated, but no matter whether you have a 2D problem or a 3D problem, you have a heat conduction in a rod or a fluid flow problem, the idea of finite difference method is to replace all derivative in the governing equation by its finite difference approximation. Okay, so now we have got this system matrix A. Okay, so this one. Okay, let us discuss a little bit about the system matrix. Okay, there are some remarks that I would like to make about this system matrix. So remarks about system matrix A. Okay, number 1, each row of the system matrix represent governing it's not really a governing equation. Each row in the matrix represent discretized equation for one particular node. Okay, so let us say if you have third row here, if you take this row, this corresponds to discretized equation at node 3. Okay, so similarly each row represents discretized equation for one particular node. Okay, and the second one, very important one, that the matrix is diagonally dominant. Okay, do you remember what is the meaning of diagonally dominant matrix? No. So diagonally dominant, we mean the absolute value of diagonal in a row is greater than or equal to sum of all other entries in the row. Equal to I, A, I, J. Okay. So if you take any entry in the matrix, so these are the diagonal. Okay, so these are the diagonal entries. Okay, you take any row in the matrix, take diagonal entry, for example here 2, the diagonal is 2, and if you add other the absolute values of other entries in the row, which also gives rise to 2, it means that the magnitude of the diagonal entry should be greater than or equal to absolute sum of all other terms in the particular row. Okay, this is what we mean by a diagonally dominant matrix. Here, for this particular problem, the matrix is diagonally dominant. Okay, the third one is that the matrix is sparse. Okay, by sparse, we mean a large number of entries in the system matrix would be 0. A large number of entries in matrix would be 0. Okay, for this particular problem, we have a 5 cross 5 matrix and we have 12 non-zero entries. Okay, so this does not really give a clear impression about the sparseness, but if we increase the mesh size from 5 to 1000, okay, let us say we have 1000 nodes. Okay, so that means size of A would be 1000 times 1000, which is 10 to the power 6. Okay, as you can see from the matrix is that each row will have maximum 3 non-zero entries for this particular problem. So the number of non-zero entries would be 3 times 1000, which is just 3000. Okay, all the other entries would be 0. So you have total entries 10 to the power 6. We have only 3000 non-zero entries. So the majority of the elements in the matrix would be 0. Such a matrix is called sparse matrix. Okay, the opposite of sparse matrix is dense matrix. Okay, by dense matrix we mean most of the entries would be non-zero. Okay, and the fourth one, the last point, is that the diagonal and off diagonal entries in the row should have opposite signs. Okay, so let us take so let me write this: diagonal and off diagonal entries should have opposite signs. Okay, so if you take an equation corresponding to node 3, you get 2 u3 minus u2 minus u4 becomes some f, the right hand side. Let's say it's f of x times x3 delta x square by alpha. Okay, this is the discretized equation for node 3. You can see that this is the diagonal term which is positive. The off diagonal terms have opposite sign which is negative. Okay, the physical reason for this criterion can be explained more clearly for a structural dynamics problem, okay, than for a fluid problem. So let us take, we have a beam bending example. Okay, so this is our beam. Let's take a cantilever beam. Let us discretize this into 5 nodes: 1, 2, 3, 4 and 5. Okay, and let's say that we apply a force at node 3. Okay, and the beam will bend something like this. Okay, the applied force represents the right hand side, and u3, u2 and u4 here are the displacement at the corresponding nodes. Okay, let us say that this is the final configuration after applying the force F. Let us apply some more force, let's say F1. Okay, because of the additional application of this force, the beam will bend more. Okay, so this additional deflection arises because of the additional load F1. Okay, so if you increase F at 3, u3 will increase. Okay, to have a physically possible displacement configuration, both u2 and u4 also should increase. Okay, so if u3 increases, u2 and u4 should also increase for a physically possible displacement configuration. Okay, this is possible only if this condition of having negative signs is met. Okay, so it means that we have 2 u3 minus u2 minus u4 is let's say F. If u3 increases, to have same right hand side F, u2 and u4 should also increase. Right, so that physical condition is possible only if the sign is different than the diagonal term. Okay, fine. So if you perform a discretization of any governing equation by any discretization method like finite volume or finite difference or finite element, the properties of 2 to 4 should be met. Okay, so you apply discretization to the governing equation, you should get a system matrix which satisfies the properties 2 to 4. Okay, if these properties are not met, you will not get meaningful results from your simulation, which means that your discretization is wrong. Okay, so if properties 2 to 4 are not met, you will get wrong results. Okay, so the property of the discretization matrix or the system matrix, let's call it, will tell you about the will give you a lot of information about the accuracy of the solution. Okay, fine. So in this lecture we have discussed how to discretize one-dimensional heat conduction problem using finite difference approximation. Okay, so in this lecture we have taken 1D heat conduction problem, a steady state heat conduction problem, and we have discretized using finite difference method. Okay, FDM means finite difference method. Okay, but our discussion is not complete because we have taken the following finite difference approximation for granted. So we have taken two things for granted: d square u by dx square at I is u I plus 1 minus 2 ui delta x square, which we have applied for the governing equation, and for the boundary condition at right node we have assumed or we have taken. Okay, so we have taken these two things for granted in this lecture without explaining how did we get this. Okay, in the next video the focus of the next video will be on how to obtain finite difference approximation to general first and second order derivatives. Okay, so before closing this video I would like to make one following remark. Okay, there are three famous methods to perform discretization. Okay, so three famous methods for discretization of the governing equation. Okay, there are many more. Three are very, very famous. Okay, so finite volume method, which is the focus of this course, finite element method, which usually is used by structural dynamics community. Okay, so these two methods are more sophisticated and more useful than finite difference method. They are more sophisticated plus more useful. Okay, also they are standard computational methods in commercial software packages and industries. So for example, if you take ANSYS Fluent, they use finite volume method, and if you take any structural dynamics package, they will be using finite element method. Okay, all the commercial packages will use either one of these two methods. Okay, and they are flexible to handle any complex meshes, and they are very flexible to handle any complicated mesh shapes. Okay, and the third one is the finite difference method. Okay, so finite difference method is limited in applicability. Okay, this is a big drawback of finite difference method. The reason why we start our discussion with finite element method is that they are intuitive and they are simple, both in terms of their mathematical or the discretization model, and from the coding perspective they are very simple when compared to other two methods. So this is the ideal starting point to learn CFD. Finite difference methods are the ideal starting point. Okay, so if you want to understand finite volume or finite element method, you should know some concept of finite difference method. Okay, and one more very important thing, no matter which method is used to discretize, whether you if you take an unsteady problem, or for del square u plus source term, this is the general convection diffusion equation. You can apply finite difference or finite volume or finite element method to discretize the spatial derivatives, but the time derivative is always discretized with finite difference method. Time derivatives are always dealt with finite differences. Okay, so even if you do a course on finite element, you should know finite difference method if you want to solve unsteady problems. Okay, so let us stop here.